Hello, everybody. I hope you're having a good day or a good night, whatever time it may be. This is practice quiz number 5, and I'm supposed to be sharing this one. Okay, practice quiz number 5. Um, this doesn't seem too bad. I just spent like maybe the past 3 to 4 hours trying to figure out how to do it, and it was just because I was taking a lot of time actually trying to figure it out, and I did a lot of extra steps. It's really not that bad. It could have been done in much less time, but this doesn't seem too bad. I would say that this quiz requires a lot of memorization. So if you're good at memorizing stuff, then this quiz should be easy for you. If not, you're gonna have to take some time to like maybe rewatch the videos and just get the rules down. To sum it up, it's basically just 3 rules. There is a fourth rule, and I'll do that rule at the end of the video, but it's not used in this practice quiz. That doesn't mean it's not going to be used on the actual quiz. It just means that it's not used in this practice quiz. That's why I'll just leave it at the end. So we're going to get into this now. I already have problem number 1 set up, but we're not going to start with problem number 1. We're actually going to start with some examples. These examples are found over where? It's on chapter 5 root locus analysis. It'll be at the end of the pages, so there's like four pages kind of dedicated to it. And you could check out these examples, but of course you could just watch this video, and I'm going to explain all of the examples right now. So we'll start with the first 2. Okay, so we have this. I'm going to just scroll down. And I'm going to delete all these graphs as I go because it'll just take up way too much space. And you'll be able to find the graphs anyway on the Chapter 5 root locus analysis PDF. So let's say you have a point on the graph. It's on this axis, the x-axis. It's just going to point to 180 degrees. It's going to have a line that points to 180 degrees, and that's pretty much it. Even if you have another one that looks something like this, it's over here, then it's also going to point to 180 degrees. It doesn't matter. If there's just one point on the graph like this, and there's nothing messing with it, it'll point to 180 degrees. But wait a little bit because some stuff might get a little bit funky if you include other points, which will happen on the quiz. Let's try the next few. So we have graph, and there's 2 points this time. There's 1 point over here, and then there's another point over here. Okay. If this point is at 0, let's say this point is at -5. If there are 2 points, 2 x's, they are going to make a line that goes straight up, and straight down. It goes up and it goes down. And that point will be in between these 2 points. So over here would be at -3. Okay. And let's say we have another one that looks something like this. And let's say that this is at 1 and this one is at 3. It'll do the same thing. It'll make a line that goes straight up and straight down. But this time it'll be at -2. It's supposed to be -1 and -3. Right? So you just kind of add these 2 values up and divide. But that's not always the case, and I'll go over that in a little bit. So this, let's say you have 2 points, and they're on the same point at -4. This is what you want to have happen because this is the easiest one. It'll just be a line that goes up and down on -4, right? And that's very easy to do. This is the case that you want to have happen because you'll easily be able to show where the line is supposed to be. And Yeah, that's pretty much it. The other thing that can happen is that, let's say you have like a bunch of x's everywhere, so like over here, over here, over here, over here, over here, right? Something like this, right? And you won't be able to know where the lines go. Obviously, there would be much more lines anyway, but you wouldn't be able to figure out where the line is. Uh, like if it goes straight up and down over here, if it goes straight up and down over here, right? It could be in a bunch of places. So that's where you would use rule number 5. Um, but we don't have to do that. It wasn't on the practice quiz, so I'm just gonna save rule number 5 for the end of the video. Select this, and we'll delete it. Okay. Oh shoot. Huh. That's interesting. Sorry, I just wanted to check if I was still recording for Google Meet, and it asked me if I wanted to leave the call because I'm the only one in the call, obviously. But it gave me a countdown. Um, and okay, so I actually was recording before, and the call suddenly stopped. So I was like confused as to why that happened. I thought I pressed something, but I think that's what it actually is. So I'm gonna have to keep an eye on that. Anyway, we'll go on to the next one. Okay. So we'll go with if there are 3 x's. I do have to make sure that it doesn't force me out of the call. But we'll just make sure that doesn't happen. If anything happens, I'll probably just join with a different account. That way it doesn't force me out. But anyway, we have a graph. And there's 2 points. Or sorry, there's 3 points. One over here, one over here, and one over here. Right? So if there's 3 points like this, you're going to take these 2 points and you're going to say, okay, these 2 points are the ones that have the line that goes up and down. The farthest to the left is going to go pointing to the left, right? And that makes sense. If you try to do it at this point, it'll like run into these x's. So the point that's farthest to the left is going straight out to 180 degrees. And these 2 points, in between these 2 points is where the line is. It can happen with something like this. If it was like this, right? It would just be in between these two. This one would point to 180. And it can also happen like this, where it was something like x, if they're on the same point, and this one's like this, then this one would point out to 180, and this would go up and down. Right. I think that's pretty much it. Those were all the cases. Okay. Yep, those are all the cases. Ooh, okay. Actually, no, I'm sorry. I did do something wrong over here. It actually wouldn't point straight up and down. If there wasn't a rule for that, then it would. But rule number 4 states that actually these points would do something like this. Let's say it was like this, right? This one would still point out to 180, but these two would actually curve and do something like this. Same for this one. It was like this. It would be somewhere in between, and it would curve this way. And this would go to 180, and then the last one as well. If it was a double point, this one would go to 180, and these two would curve like this. I could explain this a little bit more when we get into the mathematics and we get into the actual rule. I think we do it on problem number 2. Oh no, we actually do it on problem number 1, but just very quickly. Um, so I'll just try to keep a mental note to do this. Uh, Actually, what I could do is just draw this, and maybe I'll remember to do it later. So we'll go like that. So I'll try to go over this when we're doing problem number 1. Okay. Okay, we're gonna go over zeros now. The zeros are gonna have an open circle, and they kind of tell where the lines to go, or where the lines should be going. So the 0. Let me just see something. Excuse me. Okay. So let's say we have two x's at 0, at the point 0, but that's not a 0. We have an actual 0 over here. Okay, so somewhere in between this 0 and the left part of the graph, so this can extend even farther. Somewhere in between here and all the way that way, the two lines are going to wrap around into a circle, and they're both going to enter in. Okay, so even if it was like this, we'll put the 0 over here. So this extends way to infinity. Okay, and there's two x's like this, right? It'll come from the middle of the two x's, and it'll go somewhere over here. Okay. If it was, make sure I'm recording. Okay. If it was this, which I haven't seen this one, so this is kind of an uncommon one. If there were two circles, it would extend outwards, of course, but it would actually end in the zeros. You know, it's going to want to end in the 0, or like in this case, between the 0 and somewhere to infinity. But this one actually does want to enter into the 0. Okay. And let's say there were two zeros, right? This is the case for two zeros. If there's an x, if there's a 0 for every x, it's going to want to go into the 0. So it's like this, and it's like this. There's two zeros. So at some point in between over here, this is going to be where the lines want to go. So this line wants to go over here, and this line wants to go over here. Pretty simple so far. If the x's were on top of each other, and there was zeros over here, it just go this way, right? If the zeros were together, so they're both over here on the same point, and there are x's over here, then these would go into the zeros. And if it were like this, where there's two x's and two zeros, whoops, two zeros, they would both want to go in between these two zeros, but these are at the same point. So they would want to go at the same point. Let's say this is -5, and this was at -1. The line will come out of -1 and want to go into -5. Okay. Okay. Yeah, we could go over these last three because they're very simple as well. Oh, okay. I know what it is. So, okay. This one might be a little bit confusing. This doesn't normally happen, That's why I was kind of confused for a second, but I see what was going on. So just remember that the x will want to go, the x farthest to the left will want to go into the 0. So that does that naturally, right? Now, this point, you would say, okay, so this wants to do something like this, right? Not in this case. There's actually just one asymptote somewhere over here. So the line will actually go like this. And once again, this is explained in rule number 4, and this is kind of like the first thing that we do. So I will go over this a little bit, and I'll keep this one as well. I'll redraw it up top. But this can be where things get a little bit funky. So over here, there might be an asymptote like this, and it will do something like this, right? Or it approaches but never touches, and then the x will go this way into a 0. By the way, I should wait a second. Hold on. I should draw the points before uh, I do the graph. So let's say there are two x's like this, and there's an x over here, and there's a 0. This one would want to go into the 0. There's an asymptote, and then this happens. I'm not just making up like x's and o's. He gives you where the x's and o's are, and you have to figure out what to do with that. So, and then there's another case where it's something like this. There's an x, there's an o, x, x, and then there's some asymptote somewhere, and then we'll do something like this. Oops. And then this one will actually want to go into the O. So this is the one case where this one will try to do that. But you could figure out which x's will do that using rule number 4, which we're about to get into right now. I will draw this graph up here as well, just so that I can just basically skim over it. There's an O over here, and there's an X, okay? And then this one's going up and down somewhere. Whoops, actually. An asymptote somewhere, and it'll probably do something like this. Okay, so we have that. We are going to delete all of this. Okay, and now we're actually going to do the problem. So, for problem number 1, it says sketch the root locus plot of a system with these points. Verify the part A with MATLAB, so we're not going to do part B. Cross that out. Okay. Let's see. Where does my work start? Over here? Yes, over here. Okay. So we are going to use, we're going to start with rule number 4, and it seems to be that we always start with rule number 4. This rule. Okay, so one thing about this rule, you don't have to draw. No, okay. At first, I should explain what it is. I'm not going to go over the full rule. You could read the full rule if you want to. My job isn't to explain the whole thing. It's to make you guys understand how to do the problem. So rule number 4 is, in the most simplest way, how many asymptotes and where they are. Okay. So for rule number 4, we're going to categorize this as category A. And we're going to say that you don't have to draw this in the final drawing. All you have to know is where they are. So category A, and this is the first rule that you start with. This is if n is greater than m. N is greater than m. Okay? You don't use this rule if n is greater than m. What is n and what is m? N is how many s's are on the bottom. Wait, hold on, let me just make sure. Yes. N is if is all of these, right? This is N, and up here is M, right? So from here we can see that N is equal to 3, S plus 9, S minus J3, and S plus J3. M is equal to 2 because this is squared. Is N greater than M? N is 3, and that is greater than 2. So this checks out. We're going to use rule number 4 now. And basically this says N, first we have to find N minus M. So that is equal to 3 minus 2, which is equal to 1. This says how many asymptotes there are. There is one asymptote. Okay. So there's one asymptote. And then we have to figure out where that asymptote is being directed, right? Yeah, okay. So where the asymptote is being directed, in this case, because it's only one, it's actually theta 1 is equal to 180. The equation would be 180 over 1 times 1. And obviously that'll equal 180. So this is not too good of an example, but this is what I wanted to go over for these two parts. So we're going to quickly go over these two parts right now. Let's see. So this one, you see how there's three x's? There's supposed to be a third x right over here, right? Let's say that there were 3 x's, and we're just going to quickly do this. So n minus m. There were 3 x's and not a single o. So if that is true, oh, I should also say, these are the x's, and these are the o's, the zeros. So let's say, in this graph, right, there are 3 x's and 0 o's. So n minus m is 3 minus 0, which is equal to 3. You would have to find theta 1, theta 2, and theta 3, right? In this one, there was only 1, so you only find theta 1, which is very simple, right? But in this one, there's 3, so you have to find theta 1, theta 2, and theta 3. To find this, you use this equation, 180 divided by the number of the number you found over here. So this is 3. And the first value you multiply it is by 1, right? It's going to be odd numbers. So the first value is 1, the second value is 3, and then the third value is 5. But we'll get to that. So 180 divided by 3, I believe that's 60. Yep, 60. The second value is theta 2. So this is 3 times 180 divided by 3. This is simply 180. And then the last one is 5 times 180. Oops. 5 times 180 divided by 3. And that is 60 times 5, which is 300. Yep, 300. 300. Right? So if it were like this, right? You have this graph before. You have this graph where you have 3 x's, right? Basically, it's saying there's an asymptote going to 180. There's an asymptote at 60. And there is an asymptote at 300. 60, 180, and 300. So that is why if you have two x's like this, or sorry, two x's on top of each other, and to draw. Let me just erase this. Two x's on top of each other. That's why if you have two x's on top of each other and they're on this side, right? There's going to be one line that goes like this and another line that goes like this, right? So in the final graph, you could just draw it like this. And then this x is going to be going to 180 as per usual, right? And that's why in this first graph, it looks like that. As for this one, yeah, as for that one, this happens where n, so over here you can see there are three x's and one o. There's one o, so that means that it's n minus m is equal to 3 minus 1. When that happens, that is equal to 2. You find theta 1, and then you find theta 2. This is 180 divided by 90. 180 divided by 90. 180 divided by 2, and this is times 1. And then you have another one, which is, this is 90, right? And then you have this one, which is 180 divided by 2 times 3. And this would be, what, 90? 270, right? 270. 90, 180, 270. Yep. And that's why in this graph, you see how it goes like this. Basically, this x is doing its own thing. Right, let me just draw everything in first. This x is doing its own thing. It's going to the 0 as it wants to do. But there's an asymptote somewhere. And this doesn't, I haven't gone over how to find the asymptote location, but I'm going to do that in a second. This asymptote is, let's say, somewhere over here, right? And it wants to go to the right, but it can't. So it's just going to go down close to the asymptote. It's going to try to approach it as close as it can, but never touch it. So that's just I just wanted to quickly go over that in case that shows up on the quiz, but that does not happen here. Not every single one of those. Only this one, which is the easiest one, where you have one asymptote at 180. Okay. Now we're gonna find where the asymptote is. So this is, to find where the asymptote is, you do r is equal to the sum of pi minus zi over n minus m. What is pi and what is zi? Pi are the x's, and zi are the o's. So a few things that you have to remember. X's, I guess I could write it over here instead. This is some important information. X's and O's. I'll just do it in one color for now. X's, you can also say that is N, and you could also say that is P. So we use these symbols for the X's. And for this one, we use M and Z. This one makes sense, of course, because it's a 0, so it's a Z. Let me just draw it better. Here we go. And I think that's the only way. Yeah, I think that's the only way we do X's and O's. If there's another way we write an X and an O, I'll just show you guys later, but that's the only ways I can think of. Okay, so we do the sum of P minus the sum of Z over N minus M. the sum of p, we're going to use all of these points over here. And we're going to find, we're not going to use positive 9. We're actually going to use negative 9 because s is equal to negative 9. So we're going to use negative 9, positive j3, and negative j3 for p. And then we're going to use negative 3 for the z's. So that would look something like r is equal to negative 9 plus j3 minus j3, and then it's minus negative 3 plus negative 3 or minus 3, right? All over n divided by m. N divided by m was 1, so we'll just get that. So over here you can see these two cancel out. This turns into negative 6, and then the negative cancels out with the negative, so this becomes positive. So this is r is equal to negative 9 plus 6 is negative 3. Okay, what does that tell you? There is an asymptote over here. There is an asymptote. Actually, I never even drew the graph to start with. I'm sorry, guys. But there is an asymptote over here, something like that. And then there's an x over here, and there is 2 x's over here. I never drew the graph to start with, and I do apologize for that. But I actually do want to go over what this graph is, by the way. Because this first question is actually kind of obvious on how it is, right? So you have x's and you have o's, right? Okay, so from this graph, you should kind of actually be able to tell what's going to happen without even doing any equations. So you have a bunch of x's and you have 2 o's. So first of all, you know that all the x's want to go to the zeros. So this is going to do something like, it's going to try to curve into this part over here. Same for this one. I want to go into here. And this one is going to want to go into here as well, right? So it's going to look something like that at the end. And that's just from the information I gave at the beginning, the examples I gave. For the first problem, you should just be able to tell how it's going to look. For the second problem, it's a little bit more complicated, but we're going to get into that one. But okay, so it's going to look something like that at the end without even calculating anything. But now we're going to get into rule number 6. And rule number 6, what does rule number 6 talk about? First of all, this is a category B, so this is going to be in the final drawing. And this is step 2. Rule 6 says we want to find the angle of departure. What is the angle of departure? Okay, so if we go back into this drawing over here, you see how these x's are on the imaginary axis? The thing about that is that since they're on the imaginary axis, we don't know where this line is departing from. What does that mean? So we actually don't know what this line looks like. So let's say there's 2 zeros over here. There's 2 x's. This line could very well be doing something like this, right? It could want to leave over here and come into the zeros. It could come from the bottom. It could come on the top like this, maybe. I don't know. There's a lot of stuff that could happen, but we want to figure out where it's departing from. So basically, this is just saying, okay, so this this x over here, what is this angle, theta, right? What is this angle? What is this angle where the line is departing from? Could it be 90 degrees? Could it be 270 degrees? Could it be 184 degrees? I don't know. And we want to figure that out. To do this, this isn't too hard to do, but it can be a little bit confusing if you see it for the first time. We're going to redraw the graph. This is the graph, x, x, 2 zeros. And let's label our points. So this is P1, P2, P3. And this is Z1 and Z2. And Z1 is equal to Z2. Okay, because they're at the same point. We need to find what the angle of departure is for P1 and P2. To do that, we're going to do a test point, and you might have seen this. This is probably starting to look familiar from class. We're going to pick a test point over here, right? And this point is actually exactly at this point over here. We just draw it just so that it's a little bit easier to see. But this test point is actually at this x, right? It's in the same exact position as this x. Okay. This test point, we're going to draw some lines like this. Sorry, not like that. Like this. There should be two lines over here, so we'll do like that. And then over here, right? So we're trying to find all of these angles to find the angle of departure. I should have mentioned one thing. We're trying to find the angle of departure, so it's theta dp1 and theta dp2, right? Trying to find theta dp1 and theta dp2, but that is not the same as theta p1 and theta p2, which we will be using when doing this test point over here. Okay. The angle of departure, that is the angle this thing leaves to get into here, is not the same angle as this point. Let's say this point is to over here, right? Or to this test point. This is a little bit confusing. I don't know the best way to explain this. Maybe the best way actually is to not use the test point system. I don't know, because like I was able to understand it after a little bit, but just know that this test point is at the same location as P1. We can even do it. We could even do it side by side because that's how confusing this is. And they're the exact same thing, but I'm just not going to put the test point over there, right? So P2, we're trying to find theta dP2. P1, we're trying to find theta dP1. There is a test point over here now, ST, and this is in the same, these are all in the same location. This test point is over here, theta P1 is over here. In this graph, theta P1 is over here, but this test point is over here, even though it's actually over here. Very confusing, but anyway. There's 2 zeros, and there's P3. Okay. So, and we're trying to find these angles. So this angle, right, like this, these two angles. Sorry, I didn't draw that correctly. These two angles, right, and these are the same angles. There we go. That looks a little bit better. And this angle. Yeah, it's really just so that it doesn't become cluttered like this, and it's a little bit easier to see when you draw it like this. But you know, it can be like very confusing. So, so we want to find the angle of P2 relative to P1. This one is very easy. This one is just 90 degrees, right? Because theta P1 is at the point J3. J3, this one over here. It's at J3, and theta P2, theta P2 is at negative J3, right? So it's literally just on the same line, on the same, it's sorry, not in parallel with one another, but it's just, you just go straight up, right? So it's not too hard to figure out that this is 90 degrees, because if you just go straight up, that's a 90-degree angle. So that's 90 degrees. Same for this one. As I said, the test point is actually supposed to be over here. So this line over here is actually, once again, 90 degrees. They're the same thing. These two graphs are literally the same thing, just drawn differently. The next one to find are these zeros. The zeros are, I don't remember where the zeros are. We'll find that out. Theta Z1 is equal to theta Z2, which is equal to, it was at -3, right? Theta, yeah, s plus 3 squared. So there's two zeros at -3. So this one is at -3. Let me actually just write these down. This one is at -3. And over here, this is at J3. So what do you have to do? Well, if you go to the right and then you go up, you're going right by 3, and then you're going up 3. So what is this? This is just tangent of 3 over 3. And by the way, just to let you know, luckily in this over here, they're both 3. But in the case, and I think this comes right afterwards, right? Yeah, in the next part, you're going to use the one on the right. So like, you first do this part and then this part, right? So when you do tan versus, let's just say that this is A and this is B. This is tan of A over B. Okay, so you're going to write it like that. Don't write B over A. One other thing I want to mention, if the angle were to be, so let me just redraw the graph again. So we know that the angle is like this, right? Then you use this equation over here, tan inverse of 3 over 3. Let's say it looks something like this. They actually look like this, right? And this angle becomes like this. You would then use 180 minus tan of 3 over 3. We'll just pretend that it's also 3 over and 3 out. Okay, so if it's an obtuse angle, you do 180 minus the tan inverse. If it's an acute angle, then you just do tan inverse. Okay, do that. Tan inverse of 3 over 3 is just 45 degrees. The inverse tan of 1 is 45 degrees, basically. The next one is theta P3. Theta P3. And this one is 9 over, this one is at the point 9. So you would walk 9 steps to the right and then 3 steps up. So this one is a good example of what I was talking about before. Tan inverse You put the 3 on top, and then you put 9. Okay. This would give you a value of, you would have to use your calculator to solve this out. It gives you a value of 18 degrees. 18 degrees. Okay, cool. After you do that, you have an equation to find theta dp1. Theta dp1. Okay. To find theta dp1, you do the sum of the theta zi. So basically these two. You add these two up. You subtract it by theta pi. So this one and this one. Also, by the way, just to let you guys know, we did not find theta p1 because the angle is 0, right? It's on the same point. If you were to find theta p1, it would just be 0, so you just don't include it. And so you do that, and then you do plus r times 180. This confused me a little bit as to like what r is. R is what you found over here, right? Over here, right? So this is your R value. Actually, no, sorry. R is something different. R is actually these, right? This times one thing over here. Remember, we did 1, 3, and then 5, right? So if you were doing multiple of them, you would multiply it by R, but it doesn't really matter because if you multiply R times 180, right? So it would be, let's say, 3 times 180. And then you subtract that by 360. It's in the same place. So you don't actually have to include R. You just say, over here, let's do this. Okay, do that. You're just going to say plus 180. Just basically ignore everything I just said. If you got confused by it, just ignore it. Honestly, just put plus 180 over here, no matter what situation you're in. And we're going to do, so we're going to do that. We found these values already. So it's going to be, I could write it, I could expand it out, by the way, just so that it's a little bit clearer. Theta z1 plus theta z2 minus theta p2 minus theta p3 plus 180. Okay, so that's the equation we're using. We're going to do 45 plus 45 minus 90 minus 18 plus 180. So the angle of departure is 162, and we're going to draw this. 162. We're going to draw this in a couple of seconds, but before we do that, we have to find theta dp2. So theta dp2, it's in the same location, right? It's in, it's basically in the same location, just on the opposite side, flipped on the x-axis, right? So all you have to do is just make it negative theta dp1. Negative theta dp1. So if you ever have 2 points like this, they're in the same location, right? It's just that one is flipped over the x-axis. And you say this is P1, this is P2, right? Theta dp2 is just equal to negative theta dp1, if this is theta dp1. Okay. So it's just always the inverse. So this is negative 162. Let's draw that just to kind of explain what's going on. Actually, we can draw the final image from this. So we'll do 2, just so that I can explain what we just found. So we had 2 x's over here, right? Let me draw this one a little bit higher. We had 2 x's over here, and we had 2 zeros. We knew that these x's were going to go into the zeros, but we didn't know what angle they were coming in from. Now we know that it's going to be at an angle of 162 degrees. So let's say, so if 180 degrees is a flat line, right? 162 will probably be something like this, I guess. This over here is 162 degrees. 162. So I would say it looks something like this. So this is how the line is departing from that x point. So to draw the whole graph, oops. But to draw the whole graph, it was like this. And then there's an x, 2 zeros. So this x wants to go into these 2 zeros. This is leaving at 162 degrees, and it's going to curve into this. This is leaving at negative 162 degrees, and it's going to curve into here. Okay, and that's the answer to the first problem. As I said before, you can kind of just see how to do this problem right from the beginning. You can see what the answer is, but you don't know the angle of departure. So in some cases, you might actually get something that looks something like this. Hold on. You might get something that looks like this, but you won't know until the end, until you find the angle of departure. Luckily, in this case, that is not the problem. So with that being said, we can now go on to problem number 2. Let me get problem number 2 up. Problem number 2 is a little bit harder, which is better because now I get to show you all the steps. I'm actually debating on whether or not we should do problem number 2 or problem number 3. Problem number 3 is the easiest because you're just calculating the angle of departure and calculating the angle of departure of this one, which is just the inverse of this one. So let's start with problem number 3 because it's easier. Yeah, so problem number 3, calculate the angle of departure from the pole at P1 is equal to negative 5 plus J5 for a system that, using the result part A, find the angle of departure from the pole at P2 is equal to negative 5 minus J5. This is why it's important to read the problem. If you just try to solve this problem, you'd be in for a hell of a time, honestly, because this is a very long problem, but you only have to do literally one step. So let's do that one step. And this will give you a little bit more practice with angle of departure. So we're doing problem A. Let's draw the graph first, of course. You draw it up here. So there are 2 zeros at negative 1. Two zeros at negative 1, and there's 3 points. X over here, another X over here, and another X over here. Okay. And we're going to label these P1, P2. I like labeling the top one P1 and the bottom one P2. Z1, Z2. You can label them whatever you want, but that's just what's easiest for me. We're not gonna do the whole test point stuff. We'll just say that the test point is over here, ST. I don't really care too much for the clutter. So theta P2, that is just right below it, so it's 90 degrees. Theta P2, 90 degrees. I didn't draw all the lines, but that's fine. Okay, and then there's this one. So remember what I said before, that if the line is obtuse, then you do 180 minus the tan inverse. Well, that's what's happening with the zeros right now. So we're going to say theta Z1, which is equal to theta Z2 is equal to 180 minus tan inverse of, and then we have to find what these values are. So if this is, if 0, okay, Z1 and Z2 are at -1. And P1 is at S plus 5 minus J5 and S plus 5 plus J5. Then that would mean that this is 5. This is -5, I mean. This is -1, and this is at 5. So basically, you walk 4 steps to the left and 5 steps up. So that would mean that this is 5 over 4. That looks like, there we go, 5 over 4. 5 over 4, and that becomes 51 degrees. Finally, you find theta P3. This is inverse tangent of 5 over 5 because it was at 10. Right? Yep. S is equal to 10. S is equal to -10. So you walk 5 steps to the right and 5 steps up, and then you get a value of 45 degrees. After that, okay, so basically, after you found that, then you find theta dp1 using that same equation. Theta dp1 is 51 plus 51. Actually, should I rewrite? No, you guys already saw the equation before. I could scroll up though. It's the theta, all the 0 values minus all of the regular points, the x's, plus 180. So it's 51 plus 51 minus 90 minus 45 plus 180. Okay. So this gives you a value of theta dp1 is equal to 147 degrees. And to solve part B, this is very simple. Theta dp2 is equal to negative theta dp1, which is equal to negative 147 degrees. So this is one of those cases that I was saying before where it could actually come out from the opposite side. So I don't think you have to draw the graph because he's only looking for the values of the angle of departure. But okay, so you have an x over here, right? This is going to go straight into the zeros, and you have 2 x's over here. So this is 180 degrees. This is like 135, right? So 147 is like somewhere over here. Just a little bit more than 185. So we're going to say that this is 147 degrees. So this one is leaving like this, and it's going to wrap its way around over here. Same for this one. It's leaving like that, and it's just going to snake its way back. Okay. So that's problem number 3. That one's a very, very simple problem. but it shows you a little bit more about angle of departure. The next problem is quite complicated. Let's do problem number 2. I wish it was just problem number 3 and problem number 1. That would be a very easy quiz. But we can't always have it easy. Let's see. Let's not do that. Let's just go over here. This much. Okay, cool. So, problem number 2. Sketch the root locus plot of a system with all of this. Verify the part A with MATLAB. Okay, so we can just cross this out because we're not going to do this. Okay, problem number 2. Oh, I forgot to take out the trash. Oh well. Oh, I forgot to wash my clothes. Okay, I gotta do that later tonight. Anyway, problem number 2. Okay, so we're gonna draw the graph first, just so that we can see where everything is. It looks something like there's no zeros in this problem. There's two x's at -1, and then there's another 2 x's at positive. Sorry, it's 5 minus -5 plus j5, and this one is at -5 minus j5, right? Okay. And this is one of those problems where you probably don't know what it would look like from the start. I can't even give you an idea of how it would look at the end. I'm pretty sure, though, that there is a line going this way, right? Oops. A straight line going up and down, but it's going to have to curve maybe something like this. You know? But we will figure it out. The first thing you do is rule number 4. So, as we said before, n is greater than m. So there are 4, n is equal to 4, and m is equal to 0, so n minus m is equal to 4. After you do that, you do this. You find all the theta values, theta 1. This is for finding the asymptotes, by the way. Theta 2, theta 3, and theta 4. You do 1 times 180 divided by 4. By the way, all of this, this is just kind of like just true, no matter what. And by what I mean by that is, hold on a second. Let me just do it. 3 times 180 divided by 4 equal to 135. 5 times 180 divided by 4 equal to 225. 7 times 180 divided by 4. So yeah, as I was saying before, this is like true no matter what. So if you want to commit this to memory, you can. If n minus m is equal to 4, you will always have these 4 angles, right? 45, 135, 225, 315. If n minus m is equal to 1, you'll only have 180. If n minus m is equal to 2, you'll only have 90 and 270. If n minus m is equal to 3, it'll only be 60, 180, and 300. You don't have to commit it to memory, but you can if you just want to memorize these numbers. Either way, like these equations are pretty simple, right? So You might want to write it on the quiz. You might just want to write theta 1 is equal to 45 because you already know it's 45. I don't know. That's up to you guys. R, or maybe you just want to write the first one. I'm sorry. Maybe you just want to write one of them. So like for theta 2, you'll write the equation 3 times 180 divided by 4, and then theta 3, theta 4, you'll just write 225 and 315. Anyway, we're going to find R. Where are the asymptotes coming from? R is equal to this minus the sum of the zeros, but there are no zeros, so we'll just say 0. N minus m, which is equal to -1 minus 1 minus 5 plus j5 minus 5 minus j5, right? So we have all of these divided by 4. R, also, by the way, I just want to mention, remember that we're not using positive 5 minus j5. What you have to do is you have to solve out for s. So s is equal to, whoops, it's asking me if I want to stay in the call again. Okay, stay in the call. So you have to solve out for s. So that's why it becomes -5 plus j5. There's also -5 minus j5. Right? That's why it's negative and not this positive value over here. Okay, so we have these. These can cross out, right? -5 minus 5 minus 1 minus 1 is equal to -12. Divided by 4, that is equal to -3. So all of these asymptotes over here, all 4 of these asymptotes are at the point -3. So let's draw that. So you have something like this. And you have an x over here and an x over here. So at this point, there are 4 asymptotes. They go in this direction, this direction, this direction, and this direction. Now, I do want to make something clear. So this line basically has a value of, it has a slope of 1. So do not draw the line like this. So let's redraw this. Right, don't draw the line like, oops, hold on. I gotta draw this a little bit better. This and like this. Do not draw the line like this, right, where the x's are inside. These 2 x's are inside this x over here, right? It should be outside, because if you were to do the slope, you would find that the x is above the line, above the asymptote and below the asymptote. So this over here is wrong. So a big red X. Okay. So the graph looks something like this. And as I said before, there's probably, no, not probably, there is a line that goes straight up and down, but we know now that it's going to look something like this. Right? And it's going to constantly approach the asymptote, but it's not going to happen. There's no dice. So we have that. Now we can find the angle of departure. Let's see how this line is leaving. Okay, to find the angle of departure, we do this. We draw the graph again. 2 x's over here. Once again, we're going to put the test point over here just because it's less complicated. If I just put it at that same point, there's going to be 3 angles like this, right? These two are equal to one another. This is Z1, Z2, this is P2, P1. P1, of course, is, or theta P1 is 0, so we don't include that. Theta P2 is equal to 90 because it's straight above it. Theta P3, hold on a second. Oh, I think I meant, wait, first of all, this should say, I think I meant to say theta Z1. Theta Z1, which is equal to theta Z2, is equal to 180 minus tangent of 5/4. Let me just make sure that I'm doing the right one. Let's see. This is, it goes 5 up, and it's 4 because this is at -1. Yep. Okay. So that's what that is. It's an obtuse angle, so you do the 180 degrees, and that gives you a value of 51. Theta E3 is equal to 51 degrees. Okay. Then you find theta dP1, which is -90. Whoops. -90 minus 51 plus 180. That gives you a value of 12 degrees. 12 degrees? Sorry, -12 degrees. Theta dP2 is just theta dP1 negative. This is positive 12 degrees. Okay, so from that, you now know this. I'm just going to draw these two for now. And I'll draw in the asymptotes, because why not? So, I drew that wrong. Okay. So, this line is going to leave at -12 degrees. -12. So this is your line, right? This is 0 degrees, and this would be like -12 degrees. It'd probably be smaller than that, but we'll just say that this is -12 degrees. So this line is going to leave somewhere like this, and this line is going to leave somewhere like this, and we know that it's going to like curve somewhere over here, right? But one thing we don't know, and we're going to figure out, this is kind of, this is rule number 7 that we haven't talked about yet. So it's going to leave at those 2 points, but where is it going to hit the imaginary axis? Actually, I probably shouldn't use the axis. It's going to hit it over here, over here, over here. We don't know. We know it's not going to hit it over here, of course, because it can't cross the asymptote. But it could go anywhere, honestly. So we're going to figure that out now with rule number 7, whole new rule. The reason why it took me so long, by the way, to do this, it took me like 3 or 4 hours, was because I thought you had to use rule number 5, rule number 6, rule number 7 for every single problem. And I was wrong. You don't have to do that. You did not have to use rule number 5 and rule number 7 for problem number 1. And I was like, why the hell is it giving me these answers? And then I realized it was a logical problem, and we knew where the lines were going. It was going into the 2 zeros on the graph, and I completely missed that. It went right over my head. So don't do that on the quiz. Look at the problem, see if you could do it just visually, and if you can, well, then you can skip out on some rules, right? You may only have to do 2 or 1. Anyway, we'll do rule number 7 now. So what we're going to do basically is just, we're going to add 1. 1 plus k times 1 over and then you just rewrite the equation, right? 1 over. I already found, okay, so you're going to rewrite this equation, and you're also going to multiply everything together. Very annoying, but you're going to have to do it. I already did that, and I don't want to do it again. It's pretty simple if you really think about it, if you just multiply it. But I'll give you the answer. So it's s to the fourth plus 7s cubed plus 61s squared plus 105s plus 50. Okay. So that's basically how it looks after you multiply everything together. You can check me on Symbolab. You can check me using your calculator. My suggestion, maybe have like a really good calculator for the quiz, because that was really annoying to do by hand. And I still had to check myself on Symbolab. And of course, you can't use Symbolab for the quiz. You can only use your calculator. So maybe bring a really good calculator that can solve that, right? Because I don't know of any calculator. Well, no, it probably can do the whole like J and S. All you have to do is replace S with an X on the calculator. But I don't know. Give it a shot. Okay. So that happens. And, well, of course, we want to just like have everything with the same denominator. And of course, the best denominator is 1. So we're going to multiply both of these by this equation, which I'm not going to write. So I'm just going to draw an arrow saying that's being multiplied. And basically what happens, this would cancel out. This would cancel out with the equation over here. And then that equation is multiplied by this 1. So it looks something like this. S to the fourth plus 7s cubed plus 61s squared plus 105s plus 50. Doesn't really look like a 5. Bothering me. That doesn't look like a 5 either. 105s plus 50 plus k, because the k, as I said, it got the equation got canceled out, so it's just k plus 1. So we put the k at the bottom, or sorry, on the right over there, with the 50 because it doesn't have an s. Okay, so we have that now, and we are now going to do this thing. You guys remember this? This was fun. So the fourth. I don't remember what it's called though. I never learned the name of these things. Oops. Third, that's the first. 0. And then we're gonna do. Actually, you know what? Why don't I look it up? Because I'm interested now. This was called steady state errors. Is that what it was called? No, it would be stability, right? I would normally say, you guys can skip this and you could just like go to the video ahead. But no, you guys should watch this. Just sit there and just wait for me to figure out the name of this system, because this was a pretty cool one. And, oh, okay, I found it. It was called Ruth Hurwitz Stability Criterion. Ruth Hurwitz Stability Criterion. This was a pretty fun lesson. This is kind of like the last fun lesson, right, where it was like pretty simple and I got it like straight away. But then stuff got really complicated after this lesson, and I was just like, man, this is getting way too hard. It's taking me like 3 to 4 hours to figure out how to do the practice quiz. But you know what? This was fun to do again. Not really, because I kind of forgot how to do it. But you know what? I figured it out in the end. And I'm here to teach you guys how to do it once again. Okay. So we have this, and it's going to be okay. So you just write, the values up here, the coefficients, and you do it. So this is the s to the fourth. So you write the even coefficients. So it's 1, 61, and 50 plus k. 7 and 105 for the odd ones. And by even coefficients, I mean the exponent with even numbers. Okay. You're going to find B1, B2, C, and D. Okay. Let's do this together. So it's going to be 7, B1 is equal to 7 times 61 minus 105 times 1, but I'm not going to write that in, divided by 7 because I'm running out of space. B1 is equal to 61. B2 is a very, very long one. B2, let me just write 61 over here. B2, I lied. B2, B2, you use this rule. Remember this one? This is B2, 50 plus K, right? Because it's always, it always goes like that. C is a very long one. C is equal to 61 times 105 minus 7 times 50 plus K divided by 61. Very big number. Very big numbers we're using. And that is C is equal to 6055 minus 7K divided by 61. Cool. So I'm not going to write that again because that was too long. D is, of course, you follow this rule again, 50 plus K. Okay, I have that. Now we're going to find where the system is stable. Do I even have to do this? I'm not too sure if I have to do this, but we'll do it anyway. So we kind of check the C and the D. We're going to do 6055 minus 7K divided by 61 is greater than 0. If you multiply the 61, it is multiplied by 0, so that goes away. You add the 7K, so it becomes 7K is less than 6055. And then you do K is equal to 865. This one, it's easy. Um, 50 plus K is greater than 0. If you just subtract the 50, it becomes K is greater than negative 50. Okay. So, oh, wait, did I put equals before? I meant to say less than. So our stability region is negative 50 is less than K is less than 865. Okay. So we're going to plug in 865. Actually, okay. So he says that we're going to redraw this, right? But we're going to plug in 865. So s cubed, s squared, s to the 1, s to the 0, every time we see k, we plug in 865. That is 161, 915, 7, 105, 61, 915, 0, and 915. And wait, did I just... Did my phone just ring? Yeah, I think it did. Anyway, because there's a 0 here, we go to the one above it, right? And we do this whole like PA times S is equal to 61 S squared plus 915. And from that, we can find where it hits the system, where it hits the imaginary axis. I'm sorry. So if you were to solve this out, you're supposed to set it equal to 0. So set this equal to 0. It becomes 61 S squared minus is equal to negative 915. And then you divide 61. So that becomes negative 3.87. And then you take the square root. So this becomes S is equal to plus or minus J 3.87. Okay. So this is where the lines hit the imaginary axis. So let's finish this off and draw the graph. So we have two x's over here, whatever they were. I think it was -5 plus and minus J5. We have another 2 over here at 1. We're not going to draw the slopes, or sorry, the asymptotes in, but it would be like over here, right? I'm just not going to draw that in. And okay, so this is at J5, and this one is at -J5. Over here, it's going to hit the imaginary axis at around here, which is -3.87. And over here, positive 3.87 J, of course. It's going to hit the imaginary axis here. So let's draw these two lines first. So it's leaving at -12 degrees. Oh, whoops. Maybe like this. Okay. So that's one line. And this is another line. And we'll pretend that the asymptote is like also over here. So this line going like this, and it's always approaching the asymptote but never touching, and like this. And that is the answer. That is actually just straight up the answer. It's leaving at -12, and the other one's leaving at +12. This one is approaching the asymptote. It also, by the way, for the other one, it hits the imaginary axis at J 3.87 and -J 3.87, which I think I cut off that negative. Yep. And then, you could see there's two x's at the same point, and it just follows the imaginary axis. You don't have to figure out, I don't think you have to figure out where those hit the imaginary axis, because it doesn't really matter. But yeah, that is pretty. Oh, I almost forgot. Rule number 5. How do you do rule number 5? Okay. This is a little bonus. If you guys want to take the chance and say, oh, he's not going to put in rule number 5 on the quiz, then take the chance. I don't really care. But if you don't want to take the chance and you want to like figure out at least a little bit about how to do rule number 5, I'm not going to go too in depth with it. But if you want to, let's try it out right now. So for rule number 5, this is basically this rule. So like let's say we had some, x's. We had some x's, right? But something went wrong, and we only have like one x over here, and there's like another x over there, or something like that, right? And we don't know where this like up and down line is, question mark. We want to find where this question mark, where this line is. I'm just going to use one of the problems from the other question, but I'm not going to use like this graph over here. This is just the example problem. To do rule number 5, we're going to go back to question 1, which is over here. We're going to use these values. So we're going to use NS and DS. Oh, okay, here it is. That was the last thing that I was trying to figure out. There is something known as hold on. Okay. So this is DS. And this is NS. This is also the most complicated out of all the rules. So that's why he might not put it on the quiz, why he didn't put it on the practice quiz. This is kind of complicated to do, not gonna lie. So this is NS and DS. NS are the X's. Sorry, NS is the zeros, and DS are the X's. So what you have to do is you're going to use this formula, NS times DS, times DS, sorry, D dot S, minus N dot S times DS. So with that being said, using the numbers from question number 1, and as I said, you don't have to use this rule because we know where it's departing from. We know where all the points are departing from, and we also know where they enter into. But if you don't, also another case this can happen is if it's something like this, where it's like x, and then there's 1 0 over here, or let's say, yeah, there's 1 0 over here. It could be anywhere from here to infinity, right? So like enters into here. We don't know where it's actually entering in from, so this is where you use rule number 5. This is an even better example than the last one that I gave. So what we would have to do is first we find NS. NS was S plus 3 squared. Yep. S plus 3 squared. DS is equal to S plus 9, S minus J3, and S plus J3. This is also another reason as to why he wouldn't put it on the quiz and why it took me so long to do this problem was because I did actually solve it out. so over here, NS is by hand, by the way. I did check it with Symbol Lab, but I did this by hand. S squared plus 6S plus 9. DS was S cubed plus 9S squared plus 9S plus 81. After you find, I meant to say dot. The derivative. No, wait. No, actually, my bad. I haven't found the derivative yet. This one was. Oh, no, this one was fine. Oh my god. Okay, anyway. 9s squared plus 9s plus 81. Now to find n dot s. This is 2s plus 6 d dot s. This was negative 3s squared plus 18s plus 9. Now to use this equation over here, which I'll just copy it. You would have to solve this equation out too, and I'm not gonna, bother you with all the calculations. I'll just give you the answer: s to the fourth plus 125 cubed plus 72s squared minus 405. After you use that equation, you might think like all of that was hard. Okay, or maybe you thought it wasn't hard because I just did it in a couple of seconds and I didn't show you like the 30 minutes it took me to figure this stuff out. But if you did think that was hard, uh, wait till you see this next part. You have to find the roots of this. And to find the roots, I can't even find the roots, to be honest with you. You would need a calculator to find the roots. A very, very good calculator to find the roots as well, or Symbol Lab. But I think if he were to give us a problem like this, it wouldn't be this hard of an equation either. I think he does do a problem like this in the examples and some for homework. And it's a much smaller equation. It usually goes up to s squared, and that's it. But if you did have to find this, you'd have to find the roots, and the roots of this are s is equal to 3. Sorry, negative 3. S is equal to negative 3 plus 6i, and s is equal to negative 3 minus 6i. Basically, you choose the farthest point to the left that is on the x-axis, and you just disregard these three. And you say, okay, this is the point where everything is entering or leaving, right? And, I thought that, and I was like, that is, okay, interesting. And I looked at negative 3, and I was like, okay, well, where's negative 3 on the graph? Negative 3 was right over here at these 2 zeros, right? It was right there the whole time. And I knew the rule too. I knew that if there were 2 zeros in the same place, that is where it's going to be entering and leaving. But I just completely went over my head because I did not draw the graph at first, like I did for you guys, which should be over here. Yeah, over here, right? I drew this graph for you guys, and I was like, oh my god, I forgot to draw the graph for you guys. Always draw the graph first because it'll help you figure out which rules you're going to use. It seems like you always use rule number 4 and rule number 6, but just in case, just draw the graph out first, see which rules you're going to use, and then start the problem. But that's pretty much it. That's all I have for you guys. I hope you have a good night. I hope you do very well on this quiz. As I said, there's just quite a bit of memorization, but it's the same steps every single time. So it should be pretty easy, and I hope you guys have a good day. I will see you later. Bye-bye.